Hello, and welcome to our program, Astronomy for Everyone. The topic this month is In the News. And here to tell us all about the interesting topics is our own Stephen Uitti.
Thanks for being here.
Oh yeah, well, you're always here anyway.
Well, it just feels like that.
So our first story concerns how young galaxies grew their magnetic fields faster than previously thought.
Pretty interesting theory, and for a long time, theory has suggested that galaxies would grow at a certain rate, and their magnetic fields would grow at a certain rate. And now that we have telescopes like the James Webb that can actually go ahead and look at these things and measure them, it turns out that no, they're much stronger than they should be. So you know, what do we do when that happens? We have a group of people study it and look to see what might be going on. So the main thing is what happens when you're doing a simulation of a galaxy and you're studying especially the magnetic fields. What happens to the magnetic fields, and in the galaxies, you're not expected to have big, 100 light year long single magnetic fields right away. You might get that much later. But the deal is that it depends on really the details of how you simulate the magnetic fields. If you do it with a fine enough detail, then you have the eddies and things like that simulated, and they in turn accelerate or improve the power of the dynamo, which the standard theory has for generating the magnetic fields. These eddies, the faster that they turn around in circles, the stronger the magnetic field gets, and it sort of accelerates the thing, and it sort of feeds back on itself. And so early galaxies look like they must be older than they are. They just grow up faster.
Because of this electromagnetic effect.
That's right. We've got plasma going on, and we've got magnetic fields, and we've got electric fields, and we have gravity. It's a fairly complicated thing that we've only, in the last 5 years or so, gotten a handle on how to do a computer simulation. We've had computers that were good enough for maybe twice that long, but the actual code, it's complicated code, and getting it right is not that easy, so we finally have it.
I've been watching the news, I'm sure all of our viewers have, and fireballs are streaking across the sky have seemed to increase lately. Just how common is this?
Yeah, so the story was there was a recent fireball that was seen in Wisconsin all the way to Maryland. It's like a long trail. And people asked all kinds of questions on it. And one of them is, how big was it, right? And it turns out to be about 6 feet in diameter, maybe. And it's like 7 tons. And it really doesn't even matter if that's metric tons or imperial tons.
It's a lot of tons either way.
No, the numbers aren't that different, and they're both well within an estimate. So, in any case, no fragments have been found because it was an asteroid. An asteroid is a chunk of rock, or it could be metal or ice, but typically it orbits the sun, but it doesn't have to, and it's leftover debris from the formation of the solar system. And these chunks of rock, etc., they can get smashed into and break up for various reasons, and you might have a smaller unit, and they might call that a meteoroid, right? So that's a fragment of an asteroid, and then you have a meteor, and a meteor is a meteoroid that is going through the atmosphere, and you see a streak of light. In the meteor showers, like the Perseids, which are real big in August, especially in the middle of August, the 13th is usually the peak. But you have a lot of these little streaks, and they're caused by they're the size of a grain of sand-ish. They're a little bit bigger, a little smaller. But what you're seeing as a streak of light is air being compressed in front of the object, not the object itself. You don't see anything about the object itself. And they're really fast. They go from anywhere from maybe 25,000 miles an hour, which is pretty fast, to 75,000 miles an hour. So the compression is really quite high, and if it has a fair amount of volume and mass to it, then there's a lot of stress on this object. So you have material burning away and fluffing off, and it's et cetera. So then what we want to know is, how often do you get these things? So the little meteorites in the showers, they just rain down. There's no counting them. But the big fireballs that, like this one that, I keep thinking, oh, it was in Ohio. Well, I have a picture that I saw, and it was from Ohio, of this thing flying by. But yeah, you get a fairly big rock like that, and how often does that happen? And the answer is an awful lot more often than you'd expect. There are a couple of organizations. There's an American Meteor Association, and there's an international version of that. And they got a couple hundred reports already by mid-March for that calendar year. And it turns out to be about one a week. So people see them on the order of one a week, but every day there are at least 3 or 4 meteors, fireballs. But most of them are over the ocean, or they're over places that aren't inhabited, like Antarctica or a big desert or something. And people don't see them because they're just not there, or maybe it's cloudy or whatever. For whatever reason, they don't see them. So the every now and again you see them is still once a week.
Okay, so that's a weekly average. Interesting to know. We'll have to keep looking towards the sky. Now, for our next story, astronomers have struggled in the past anyway, or up till now, to tell the difference between a gas giant exoplanet, a planet outside of our own solar system, and a brown dwarf, which is basically a failed star. How has a recent study changed this?
So we can now tell the difference. And by the way, it's not just an exoplanet that's orbiting another planet, because you can have a rogue planet, something that's been ejected from a stellar system.
Okay.
I mean, we just had our third interstellar object, a comet, so 2 comets and who knows what it was. And these things were very likely ejected from some solar system somewhere. And we think that this happens on a daily basis around the galaxy, and so there are an awful lot of these things floating around. In any case, getting back to the subject, so you can have exoplanets that are rogue, they're not in a solar system, and you can also have brown dwarfs that are either in a solar system or not. And so you still want to be able to tell the difference. And the new thing that they've done, and they've done a recent study to sort of firm it up, is the spin rate. Jupiter spins in about 10 hours. It has a day of about 10 hours. Our sun, the sun, takes about a month to do one rotation. It's a lot slower, right? Rather than like more than twice a day, Earth day, it's 30 days, right? Anyway, so they've compared a bunch of exoplanets and a bunch of brown dwarfs, and they found that there's this same thing. The exoplanets spin pretty fast, a high percentage of their maximum rotation rate, beyond which they'll fly apart. They're not, Jupiter isn't going to fly apart anytime soon, but
good to know.
But anyway, and the brown dwarfs are much slower, and they're even much slower if they're only, say, 3 or 4 times So you might have a super Jupiter, as it were, a 3 times Jupiter mass Jupiter, and you might have a brown dwarf that's only maybe 3 times bigger than that, heavier than that, and they're almost the same size, but the brown dwarf will be maybe 10 times slower than the big Jupiter. Yeah.
Okay.
So it's pretty easy to tell once you do that.
Oh, okay, great. Well, we're going to take a quick break. If you have a question, please send us an email. The address, as always, is down at the bottom of your screen. And we'll be back with more of In the News after Term of the Month.
Thanks, Don. The term of the month is radio broadening. I volunteered idle computer time on my computer to SETI at home starting in September 1999. It was a project to search for alien radio signals. They had to have some assumptions, and one of them was we send signals at around 1 hertz of bandwidth for our intentional signals. If you widen the bandwidth, then you have your power distributed over that wider bandwidth, and it's less powerful. It's harder to detect. So they went by searching 1 hertz of bandwidth at a time. Now, if you're looking at 200 megahertz of bandwidth, that means 200 million little bands that you have to check. And that's an awful lot of computing time. And so there were hundreds of thousands of volunteers like me who had their computers doing this work, since not only was it millions of bands, it was also the entire sky. But the question is, could we send a 1 hertz signal over interstellar distances? And the answer is maybe not. Turbulence from the host star can broaden the signal from 1 hertz to 10 hertz, or even 100 hertz, just leaving the immediate solar system. Broadening to 10 hertz reduces it to 6% of the original strength. Researchers looked at signals sent by a variety of our spacecraft and calculated the sun's effects. Then they extrapolated to other stars that have different characteristics. For example, red dwarfs make up 75% of the stars in the Milky Way. But these stars are notoriously violent, and so they'll have much larger spreading. So what can be done? Collect more data? Yeah. Filter less? Yeah. Future observatories like the Square Kilometer Array could do matching filters and multi-resolution channelizing to detect smeared signals. It's a ton of extra processing power. So maybe we'll see rainbow graphs on home computers again sometime. And that's Term of the Month, radio broadening. Back to you, Don.
Thanks, Stephen. We're back with our discussion of topics in the news. So, Stephen, I hear that there's an update concerning the DART mission.
Sure, the DART mission. That was Didymos is the big asteroid, and Dimorphos is the asteroid, as a binary pair, is the asteroid orbiting it. It's a smaller rock. So the update is some analysis that was done from DART mission data, and in particular, it was pictures, and they saw on Dimorphos, the orbiter. They found these sort of wavy lines, this sort of fanning-like pattern in the dirt, and they wondered what that might be, and they came up with some ideas. Could it be electrostatics? Because that's a big thing on the moon. It can actually levitate material into, not the air, because there isn't any, but can levitate stuff
up
above
from the surface,
up from the surface, and these asteroids are smaller. So if that's a thing, then you would think that there would be a stronger effect. But they ruled it out because it couldn't seem to create that kind of a pattern. And they looked at some other things like seismic quakes wouldn't do a little wavy pattern like that. And so they thought, well, what if it was some sort of an impact? What kind of an impact would that be? And well, there is an old idea. So so there's something called the Yorp effect. And the Yorp effect takes an asteroid and it rotates the asteroid, it spins it up, it rotates it faster and faster. And the effect comes from, you have energy from the sun, you have radiation from the sun that hits the surface, but the asteroid is rotating. So when the surface that's warmed radiates in infrared radiation, when it radiates away, it's already rotated, so the asteroid gets a little kick, and over time it spins up the body. And what can happen is you can actually get to the point where it's spinning so fast it actually breaks stuff off.
Okay.
So kind of a weird thing. So they did some calculations on how fast the material would be going, and it's not fast. It's not even as fast as a person walking. We're talking about slow here. And then what about the material itself? Well, it would be, in order to make these effects, it's not like a crater on Dimorphos. It's more like, well, I don't know what it's more like. And they said it would be like if you had a really loosely packed snowball. Well, it's not a snowball because the material, there's not much snow on either of these bodies. What they have is this fine silicate powder on the surfaces, and so you'd have a little bit of that, and it wouldn't have to be a ball, it would just have to be some material, and it would strike, if it came off of the parent, Didymos, and it struck Dimorphos, then it would be coming in very slowly, but Dimorphos has rocks and boulders and stuff, and if this stuff was sort of spraying over the surface, then behind the boulder you wouldn't have anything, but you'd have a fan out pattern beyond the boulder on one side or the other. And that's in fact what we're seeing in the photos. They weren't even sure that it's not a big effect, so they weren't even sure that it was a thing in the photos. They did a lot of work to make that determine that it really is a thing, right?
Oh, okay. So they were able to do experiments and figure out just
that's right.
what exactly was causing it.
So then they also did physical experiments where they made a simulated surface, and they dropped a pebble into it, and they had little gravel inclusions to simulate the boulders, and they got the fan patterns in this simulated surface. So it's quite a nice physical experiment. They did computer simulations, they did a lot of analysis, and they came up with this thing. And they conclude that they have 3 lines of evidence that say this is material moving that is transferred from one asteroid to another. For the first time, we've demonstrated this.
Interesting.
We thought it might happen. Well, it does.
Wow. Now, I understand there's news about a new study concerning the early universe?
So, yeah, the early universe. So we've thought about the early universe as having a primordial soup, out of which you created, as the universe cooled, you got hydrogen atoms and helium atoms, but you also got everything else too. But you didn't get the bigger atoms until much later. So what is this primordial soup? Because they didn't explain what that was really. They just
I envisioned gazpacho, but
yeah, who knows? Yeah, so they didn't explain it or what its properties were or anything. And we know it's hot, and we know it was hot, and we know it was very dense. And we have some math that talks about that, and we know that atoms formed from it and stuff, but we don't know a whole lot else. And how do you get a handle on that? Well, it's too hot and dense to have like a cubic thing of it anywhere on Earth. But there is something that is the right temperatures and has some of the properties that we expect inside the nucleus of an atom. So how do we look at that? Well, at CERN, which is the big particle accelerator in France and Switzerland, they took Z bosons, and so photons are an intermediate communications particle in electromagnetism. Believe it or not, all this light that we see is it's this intermediate thing. Well, the Z boson is like that, but for a different field, and we don't even care. So they managed to smash Z bosons together at relativistic speeds. So high energies, basically the speed of light, but just below it because it has mass. And then they look at the spray of stuff that comes off of it, and so the analogy is you've got an ocean spray, and some of it gets on shore, and you can analyze the pattern on the shore, and you can find out something about the ocean with it. So that's what we're doing here. This is not an easy thing to do, but so they did this, and after the analysis, they found evidence of ripples, waves. So if you stick your finger in some water and you move your finger, you get a wave pattern. It's what is it?
A wake?
It's a wake.
But
right?
like a boat in water.
Like a boat wake, something like that. If you do that in sand, you don't get a wake. You get a movement right away of the sand, but you don't. It doesn't go anywhere.
It just pushes off to the side. And
that's right.
Yeah.
So that's what we're seeing. So we saw a wake, and this analog to the early universe suggests very strongly that the early universe had that as a property. It's really more soupy than it is something else. It's not a solid, certainly. It's not an air.
Not a gas, right?
Yeah. So it might be a very hot plasma, but it has this property as
property of
soup,
a liquid,
of a soupy thing.
Yeah, soup.
Primordial soup, after all.
So next up, the ESA's CHEOPS mission. There's been a discovery with that.
There is a star system, LHS 1903, and 3 planets had been discovered around this star. It's a little tiny star. It's a red dwarf, so everything is real close into the star. The first one is labeled B, and then C and D, and then E. And B, the one that's closest into the star, is a rocky planet. So it's like an Earth or something, but it's, And then the 2 middle ones, C and D, they're gas giants. Well, they're maybe half Neptunes, but they're gas giants. And then finally we have E, which is the 4th one out, and it's a rocky planet. Now, in the theories of planetary formation, that's just not right. That's just like, how did it get there? What did it form somewhere else, and it went out, or whatever happened? What else happened? And but one of the ideas, and we've not actually seen this before, is that it could have formed right where it is, but it formed later than the other planets did, and by that time there wasn't any gas to accumulate around it to be a gas giant. And so all you have is the rocky core. So that's what they think.
Okay, well, that was another very interesting discovery. Steve, I want to thank you very much for taking your time to do the research, looking into these stories. Please visit our website. The club address is down there at the bottom of your screen. And coming up to finish the show is Stephen, of course, with What's Up in the Night Sky.
Thanks, Don. What's up in the night sky for April 2026? The sun goes from Pisces to Aries this month, with Venus, Mercury, Mars, Saturn, and Neptune near it. So those are all going to be difficult to see this month. Now, I think of the moon, or the full moon, as being sort of like a 3-day event. It looks, you look up in the sky and you go, oh, that's a full moon. And then the next day, oh, it's a full moon. And then the next day, it's a full moon. Astronomically, there is a moment of the full moon. And that's important this month. April 1st, we have a full moon. We have last quarter on the 10th of April. We have a new moon on April 17th. And then we have a first quarter on April 23rd. Now, there are 30 days in the month of April, and there are Februaries that almost have a blue moon, which is a second full moon of the month. So why doesn't this April have a full moon on the 30th? And the answer is, it does. It depends on what time zone you're in, because the time between the two full moons isn't quite 30 days, but if you're in Detroit, then the full moon at the end of the month is on May 1st. But if you're in Hawaii, then the second full moon is in fact on April 30th. So it's a time zone thing. I think it's horrendously crazy, but that's what we have. So it doesn't turn blue. It's just the second full moon of the month. So on the first at sunrise, we are showing Mercury, Mars, Neptune, Venus, Pluto, and Saturn. So Mercury goes from Aquarius to Pisces, and remember that the sun is in Pisces at the beginning of the month. So it rises in the morning really just before sunrise. Mercury has max western elongation on the 3rd, and aphelion, which is when Mercury is his farthest from the sun, on the 4th. So you would think that the beginning of the month would be the best time to see Mercury, and I'm not sure that there is a good time. Mars goes from Aquarius to Taurus over the month, and also rises right around that same time. And Neptune is in Pisces and all month, because Neptune is so far out it doesn't change constellations. Then we have Venus in Aries, and it doesn't change constellation either. Pluto in Capricornus, and Saturn. And all of these things are really close in together. So all of that's really kind of cool. You can actually, if you could see them, you could see them in almost a conjunction. Then on the 22nd of April, just after sunset, we have Jupiter in Gemini, and it sets after local midnight at the beginning of the month, and just after midnight, maybe an hour, maybe 2 hours after midnight by the end of the month. And then you have Uranus, which is in Taurus, and it sets just before midnight at the beginning of the month, and then maybe 2 hours earlier than that, maybe 10 o'clock at the end of the month. And that's what's up in the night sky for April 2026. Now remember, we don't charge money for this show, but we may tax your brain.